Welcome to this class on the financial performance measurement. This is part 5 of the classes on financial performance measures and it's to do with time values and operations cash flow. So in this class we'll have the following outline. First of all, we'll see how time value works both in borrowing and investment. We'll see what are the basic parameters that are affected by time value in both the activity of borrowing and the activity of investment of a company. Then we'll deal with some special topics in time value, and in particular we'll look at deferred annuities and sinking funds. And finally we'll concentrate on the operations cash flow that will be defined in greater detail. The operational cash flow has already been discussed in an earlier class, but this will be the basis for the application dynamic criterion to assess the financial performance of a project. In this class we'll have more insights on them, and so we'll discuss how they can be calculated in greater and greater detail. So let's start from the time value in borrowing and investment. So here this slide intends to show how the concept of time value applies to both borrowing and investment. And in the table that in these slides we highlight the basic parameters on which time value has an effect, that are the inflow of funds, the outflow of funds, the time preference of the investors, and the time structure of the cash flow. So, and here in the columns we have the description of these parameters for both a loan and investment. And even though these operations are different in nature, we'll see that, however, the issue of time value will be valid for both of them. So let's start from the loan. So the loan, in the perspective of a firm, will generate inflows. The inflows are mainly related to the disbursement of the amount of the borrowed capital, whereas the outflows are related to debt service. And I remind you that for debt service we mean the total payment made in each period by the firm for principal repayment and interest payment. So in the case of a loan, the time value applies in this way. First, I have an inflow that is related to the disbursement of the loan amount, and after that I have a series of payments that are represented by the debt service that can be constant or not, depending, as we know at this point, on the amortization that has been set for the specific loan. Instead, in the case of investment, we have different inflows and outflows, because the inflows are represented by the cash flows that the project generates over its life, whereas the outflows are represented by the initial investment made to start the project. So in this case, the timing is inverted as compared to the loan, because first you have a disbursement, so you have an outflow that is represented by the initial investment, and then after some time you have the inflows that are the cash flows. So the time value of money applies in a positive way to the loan and the investment, because in the case of the loan you first have the inflow and then you have the outflows, and then in the case of the investment you first have the outflow and then the inflow. So the financial dynamics, the time structure, the cash flow is exactly the opposite within the loan and the investment. And the time preference of the investors is represented in the case of the loan by the interest rate, in the case of the investment by the discount rate. So let's try to understand what we mean for time preference, and why we have interest rates for loan and why we have discount rate for investment, and what is the meaning of interest rate and discount rate within this specific setting. So So in the case of loan, we have said that the firm first receives the money, so it's an inflow, and then will pay back the principal and pay the interest. So we'll have payments after the initial inflow. Clearly, for a firm, this is an advantage from a financial point of view, as you first receive the inflow and then you have the payment of the outflow. But clearly, for a bank, you have the opposite situation, because the bank wants to be compensated for disburse the amount of the loan at the beginning and then receive only later these payments. So, and as we have discussed in the previous classes, in order to be compensated for the initial disbursement, the bank does not only require the repayment of the principal, but also requires some compensation. This compensation is represented by the interest rate. So the interest rate is going to compensate the time preference of the bank, because clearly the bank is receiving the payment after making the original payment to the firm, and so requires a compensation that is represented by the interest rate. So clearly the total sum of the payment will be higher than the initial amount of the loan, because the bank needs also a compensation for the initial disbursement. And in the perspective of the firm, instead, the interest rate is a cost, and it's a cost related to the fact that you are receiving an inflow before paying the debt service at a later moment. So the interest rate for the firm is a cost for time preference in this sense. So as a firm will receive an amount of capital before the series of payment, will have to pay a cost for that, that is the interest rate. In the case of the investment, instead, you have the typical situation where you have the initial investment and then you have the cash flows. And as we've said in the previous classes, if you want to compare the future cash flows with the initial investment, you cannot simply add them up to the initial investment, but you have to make them comparable with the initial investment. And what we have said in the previous classes is that to make the cash flows comparable with the initial investment, you have to discount them. So after that you discount the cash flow, you make them comparable with the investment, and you can subtract, add them up to the investment. But in order to discount the cash flows, you need a discount rate, as we've seen so far. So now the discount rate is something that we'll analyze more specifically in the next classes. We'll understand what the determinants are of the discount rate, when the discount rate is higher or lower. We have already talked about the cost of capital in previous classes, and we have seen how the cost of capital is related to the different sources of funding and the different costs of the sources of funding. But here what matters is that when you have to discount future cash flows after an investment, you should consider what return you could have earned on a project having the same characteristics of the project where you've invested. So the discount rate in this case is the rate of return that you will get on an alternative project having the same risk as the project where you decide to invest. And as we'll discuss in more analytic terms in the next classes, this is affected by the risk of the project. So discount rate compensates the investors for time preferences, in the sense that the investors have to make the investment immediately, so you have an immediate outflow. They will receive the cash flows at a later moment. Clearly, the fact that they receive the cash flows at a later moment will reduce their value, as we know that the investor has a preference for earlier cash flow, and so you have to adjust the cash flow based on their timing, and in order to do that you need this discount rate that, through the discounting procedures, accounts for the time preference of the investors in the project. And then finally, in order to provide an overall valuation of a loan or investment, you need to understand in an analytic way what are the phases of the different cash flows that are assigned to the loan and investment. So in particular case of the loan, you need the phasing of disbursement of the amount of the loan and of the future repayments. Whereas in the case of the investment, you need a phasing, that is a time structure of the investment that is typically made at the beginning of the project, and of the future cash flows that will be earned by the project. The phasing of disbursement and repaid jointly with the interest rate will define what is the present value of this disbursement and repay. That clearly will have to be compared with the amount of the borrowed capital. The phasing of investment or cash flow jointly with the discount rate will allow the analyst to determine the present value of the project, so to understand whether the project is financially viable and convenient or not. So these are all issues that we'll analyze in the next classes, where we see how the discounting process can be usefully applied to provide a more complex and analytic valuation of an investment project. So now we can switch to the second topic of this class, that is special topics in time value. And as I was anticipating at the beginning of this class, we'll look in particular at two special topics in time value. These two special topics are deferred annuity and sinking fund. Deferred annuity is a particular situation where you have an annuity, is the annuity that we have described in the previous class, but with an important difference, that is that the annuity does not start immediately in the next period, but starts after a certain number of periods. So it's delayed in time, will start at a future moment in time. This is a situation that can happen in some particular case, for example, when a project pays an annuity only starting at the third or fourth year. This can happen when, for example, the project requires an initial period of construction during which it's not paying any cash flow to the investors. Or it can happen when a loan is repaid starting from some future year, and this is a topic that we already discussed when we are talking about the amortization of that. It can happen, for example, that the bank and the firm negotiate for a specific project a personalized amortization that's where the payment starts only at some year in future time, because, for example, in the beginning of the life of the project, you could have financial constraints that do not allow the firm to pay back the principal of the interest. So also in this case, you could have a custom payment to the bank, but only starting from year 2, 3, or even later. So in this case, the financial problem is that you cannot apply the annuity formula to determine the present value of this series of payments. So we have to see how we can correct the formula that we already analyzed in order to get the present value in a simple way. A sinking fund instead is a method of accumulating funds for a given purpose that, for example, could be the replacement of an asset in the future time. And in this case, a series of payment is made to some financial intermediary, and you pay basically the principal, but this principal then accumulates also with some rate of return to give in the end a given amount of money. So here the problem will be stated as follows. We need a given amount of money in X years. And we want to accumulate this amount of money by making periodic payment during this period. And so we want to know what is the periodical payment we have to make in each period in order to get the final amount of money that we need at a specific time. So in next slides, we'll get into the details of these two specific situations that we have in time value. So let's start from deferred annuity. In this slide, we have an example of a deferred annuity. In particular, we have a project of 7 years where the annuity starts only in year 4. So starting from year 4, we have 4 constant annuity in year 4, 5, 6, and 7. And evidently here the project is in the construction phase, so it's not generating any payment for the investor. So a deferred annuity can be defined as annuity postponed until some future period. So now the problem of having this kind of annuity is, how do I determine the present value of such a payment? Because in the previous class we calculated the present value of annuity starting year 1. But in this case we cannot apply that formula because in our case the annuity is deferred. So that formula will provide us with an incorrect calculation of the present value. So we have to find a simple way to calculate the present value of a deferred annuity for the cases like loan repayment or investment with delayed payments where this situation happens. Well, one way to simply resolve this issue is the following. Let's consider an example where we have a discount rate of 10%. We have again a project of 7 years, and we have again an annuity starting from year 4. This annuity is equal to $8 per year for year 4, 5, 6, and 7. How can we calculate the present value of this annuity? Well, we can consider 2 other annuities that are reported in these slides of the same amount. So 2 other annuities that have a constant payment of $8, but with different length, and moreover, that starts at year 1. So these 2 annuities are the traditional annuity that starts at the first period of the life of the project, so are not deferred. This is important because being not deferred but being calculated in traditional way, you can determine their present value applying the formula that we have seen in the previous slides. So the first annuity that we have here in orange is an annuity that pays $8 each year, starting year 1 and until year 7. So you have a traditional annuity of $8 for 7 years. And then you have a second annuity. The second annuity is always paying $8 a year and always starting in year 1, but only for 3 years this time. Okay, so you have 2 traditional annuities that have these characteristics. And as you can also see from the graphical representation of this slide, the value of the deferred annuity that we have in the, here in the upper part can be interpreted as the difference between the present value of the annuity of 7 years and the present value of the annuity of 3 years. Because if you consider the present value of the annuity of 7 years and then you subtract the present value of the first 3 annuity payments, the difference is exactly represented by this 4 annuity that goes from year 4 to year 7. That is exactly the annuity for which we are trying to calculate the present value. So one way to solve the problem is taking the first annuity and calculating its present value using the formula that we already know. Taking the second annuity and calculating the present value using the formula that we already know. And then get the present value of the deferred annuity just as difference between the first present value and the second present value. And this is exactly what is done in this slide. So in this slide, we apply the annuity formula to calculate the value of the first annuity, the one in orange, that lasts 7 years. The present value is 4.868 times $8, where the 4.868 is the annuity factor for an annuity of 7 years with a discount rate of 10%. The present value of the second annuity is 2.486 times $8, where again 2.486 is the annuity factor for an annuity of 3 years with a discount rate of 10%. And so the present value of our deferred annuity is calculated here as S equal to the difference between the first present value and the second present value. This is equal to 2.382 times $8. So in this way, just applying the traditional method for the calculation of the present value of an annuity to two different annuities and calculating the difference, we have been able to determine without too many calculations, without complicating the calculation too much, the present value of the deferred annuity. And this method can be applied each time that we have a situation like that within the context of a loan or of an investment. So the second special situation that we are analyzing in this class is the sinking fund. So as I was saying before, a sinking fund is created to accumulate a fund to be available at some time in the future. So it can, for example, a firm can be aware that a given plant or other fixed assets has to be substituted in the future, or that at a given moment in time you have to increase your production capacity. This will require liquidity to be invested in the new fixed asset. And so if you're not sure that you will have this liquidity in the future, you can decide to accumulate a value over time, so with making a constant payment, and then be sure that at that moment in time you will have the needed liquidity to make the investment. So here we have an example of a sinking fund. So we have a period of generic n years, where n can be any number of interest. Here, for simplicity, we are assuming that at the end of year n, you want to accumulate a fund of $1. So the question that you ask in the method of the sinking fund is, what is the custom payment of S dollars that I have to make any year in order to get $1 at the end of year n? And in asking this question, you have to remember that when you make constant payment over time, you are not only accumulating the principal that you are paying, that is S, but you're also accumulating the return, and the return that will that you will earn on the principal that you pay will compound over time in order to get in the end your sinking fund. So in order to calculate the annual payment that you have to make in order to get the intended sinking fund at the end of period n, you have also to account for the return that you will earn on the payment that you make over time. So from a formal point of view, if you want to analyze the problem from with a formula, you can state that the payment S that you have to make over time in order to get the desired fund at year n is equal to R divided 1 plus R raised to n minus 1 multiplied by the fund that you want to accumulate. So S can be defined as the sinking fund factor that, once multiplied by the fund that you want to obtain at the end of the period, gives you the annual payment that you have to make constantly in order to get the sinking fund at the end of the period. So let's see how this formula works with a numerical example. So let's assume that at the end of the period of interest, you want to accumulate a fund of $1,000. So this is your objective, and you're assuming that the period you take into consideration in 20 years. So you want to accumulate these $1,000 over a period of 20 years, and you know that the rate of return that you get on the payments you make is 10%. So you want to know what is the payment that you will have to make in each of the year in this period in order to get this 1,000 in the future. Well, what you can do here is just to apply the formula we have seen in the previous slide and calculate the sinking factor. So applying this formula, what comes out is that the sinking factor is equal to 0.0746. And if you want to know what is the constant payment that you have to make in each of the 20 periods for which you are accumulating funds, you just multiply the sinking factor times the fund of $1,000, and so you get that you have to make annual payment of $17.46 a year in order to get a final fund of $1,000. So in other words, what we are saying is that making for 20 years an annual payment of $17.46 is equivalent to get $1,000 at the end of the period. So you are indifferent between getting $1,000 at the end of the period or having or making payment of $17.46 a year. This formula, from a logical point of view, is similar to the formula of the annuity. The only difference is that in the case of the annuity, you were calculating the equivalent present value to a series of payments. In the case of the sinking fund, you are calculating not the equivalent present value, but the equivalent future value to a series of payments that are made before that future value. So instead of being based on discounting process, the sinking fund factor calculation is based on the compounding process. And these are all processes, however, that we have studied so far and that we have analyzed in the previous classes. So at this point, we can concentrate on the last topic of this class, that is the operations cash flow. So this is a critical topic because the dynamic indicators that we'll see in the next classes and that will be used for project value assessment will be mainly based on the calculation of the operations cash flow. So the operation cash flow is something that we have to define in a detailed way and with attention, even though this is something that we have already introduced in the previous classes. So there are two preliminary remarks that have to be made on operations cash flow before that we look again at its analytic determination. So first of all, we have to consider that within a project, several resources are committed and other resources are generated. Typically, the resources that are committed in a project are financial resources and real resources, where financial resources are clearly money that is provided by investors, that is then transformed into real assets that are plants, machinery, fixed assets in general, raw materials, and so on, that then will be used in the operations and generate other real assets that are typically products and services. And so there are some real assets that are related to financial flows, but there are also financial flows and financial resources that are generated and employed in the project without corresponding to any real assets. And this is the case of the loans or the financial management of a project. When you get a loan or you pay a loan, you have a financial payment that is not related directly to the real assets that are used by a project or the real assets that are generated by a project. So the operations cash flow refers exclusively to the cash flow that are generated by real assets. And I make an example in this. So you can have, for example, a financial flow that comes either from a loan or from the sale of products that are generated, that are sold within the project. So the financial flows will anyhow be equivalent because you will have anyhow money that is created by the project. But in one case, the financial flow that comes from loan is purely financial. It's not generated by any real asset. In the case of revenues, the financial flow comes instead from the generation of real asset that is a product that then is sold. So when you evaluate a project, you want to understand what is the value of the project independently from the financial management. So you want to know what are the financial flows that are generated by the real assets of the project. And so in this case, you have to refer only to the operations cash flow. So the operations cash flow, in other words, is the cash flow generated by the real assets created by the project, and then excludes by definition the financial flows that comes from banks and other financial investors. So when we'll calculate the operations cash flow, we'll see that these items will be excluded from the calculation. The second important preliminary remark on operations cash flow is that operations cash flow is the basis for assessing the return on capital assets committed to the project. So when we'll apply the financial valuation method to the valuation of the project, we'll see that they will be mainly based on the projections of operations cash flows over the life of the project. So that's why it's very important to understand the nature and the calculation of this particular form of cash flow, because it will be the basis for the criterion that will be then applied to the assessment of a project. Then let's see at this point how the operations cash flow is calculated for each project period. In order to calculate the operations cash flow for each project period, we have to start from the cash flow, the total cash flow for each project period. And if we want to link this cash flow to what we already seen in the previous classes, this has been defined when we're talking about cash flow statements as cash flow for financial planning. So this is the total cash flow that the project is generating in a given period, and therefore is given by the difference between the total inflow and the total outflow. So in this case, in the cash flow for financial planning, we find all the inflow, both real and financial inflows, so both inflows related to the sale of products and services, and external finances such as loan or short-term borrowing. And you have all the outflows, so all the outflows that are related to the cost for production, so the cost related to real assets, but also the outflows related to the financial management of the project, so the outflow, for example, related to debt service or to the payment of dividends to shareholders. So if we want to pass from the cash flow for planning, so the total cash flow, to the operations cash flow, that is what we are interested in for the valuation of the project, we have to correct the cash flow for planning, for financial planning, cleaning this item from the financial cash flows, so that in the end we have only the financial flows that are related to real assets. So this means that all the inflows that had been considered for the calculation of the cash flow for planning, but they have only financial nature, should be excluded from the analysis. So that's why here you start from the cash flow for financial planning, and then you subtract financial inflows, where for financial inflows, as you can see here, we mean equity contribution, so the investment made by shareholders, loan disbursement, that is the money that you get from the bank at the moment you negotiate a loan, eventual subsidies and grants that have pure financial nature, and so on. So all those financial inflows that have been correctly considered in the cash flow for financial planning, because in that case you want to know what is the total liquidity generated by the project, but are not part of the operations of the project. They are not generated by the operations of the project. They are not related to real assets that the project generates in its operations. So subtracting the financial inflows allows us to clean the total cash flow for planning from those cash flows that have only financial nature but are not related to the operations. On the other side, we have to remember that when we calculated the total cash flow for financial planning, we also included financial outflows. So those outflows that were not related to the operations, so were not related to the cost for production or for commercial or administrative activities, but also the outflows that were related to the management of financial activities. So in particular here for financial outflows, we mean principal repayments to the bank for a loan, interest payments, or dividend payments to the shareholders. So these financial outflows were originally included in the total cash flow for planning, but they are not needed for the operations cash flow. because they are only related to the financial management of the project, but they're not strictly or directly related to the operation, so to the production of the project. So if we want to clean the total cash flows from the financial flows, we have to add those financial flows that were originally subtracted by the cash flow for financial planning. So in other words, if we want to summarize this process, we start from the total cash flow for planning that includes all the inflows and the outflows, independently of their real or financial nature, as we can remember from our definition of cash flow for financial planning that we gave in a previous class. But at this point, as in the operation cash flows, you want only those inflows and outflows that are generated by real assets. You have to clean the financial, the cash flow for financial planning from the financial cash flow. So you have to subtract those financial inflows that were originally added in the calculation of the cash flow for financial planning. And you have to add the financial outflows that were originally subtracted in the calculation of the cash flow for financial planning. Once that you realize these two operations, you obtain the operations cash flow that is exactly our intended result. So the procedure is this one. And however, you could have a different procedure, because you could get exactly the same result if instead of starting from the cash flow for financial planning, we started from net profit, we added back depreciation and interest payment because they are a financial outflow, depreciation because, as we know, is a non-financial accounting item. Clearly, we should account also for taxation, so we should correct taxation and correct in particular for the impact that depreciation and the interest payment had on taxation. At this point, we should subtract the investment in fixed assets and net working capital, and we will get again as a result the operations cash flow. So we can either start from the cash flow for financial planning and clean it from financial cash flows, or we can start from the net profit, add back depreciation and interest payment, net of the impact on taxation, subtract the investment in fixed asset net working capital, and you will get anyhow the operations cash flow. So why is it important to have the operations cash flow as a measure or a basis for the appraisal of the value of the project? Well, because the operation cash flow allows us to understand what is the return that the project is generating from its real asset. So in other words, in the project is using some real assets that the total of real asset is defined, as we already know, as invested capital. So there is a total invested capital made of real assets. These real assets are generating financial flows, that is, by the way, exactly operations cash flow. So we want to know what is the cash flow generated by this real asset that express the real return on the invested capital that the project is able to guarantee to its investor, independently of the financial management, so independently of how much money will be invested by shareholders or will be raised as loans from banks. So this is a critical point that we'll have to keep in mind for the analysis of the dynamic indicators that we'll use for project appraisal in the next class. So this class has ended. I thank you for attention, and as usual, I remind you that you can find additional materials on the topics of this class on the course website.